Welcome to the Decode Podcast with Elias Malfavon, Daniel Stanphill, and Sean Kincaid.
Thank you for tuning in today to the Decode Podcast. Mr. John Burke is our guest today. His bio says Santa Clara, California, but I don't think he's there now. Something tells me he's in Vietnam, but we'll get to that in a little bit here. He's the president and CEO of Vietman LLC, which is a global manufacturing organization helper working on streamlining production and increasing yields. He holds more patents than we have time in this show to discuss. I viewed some of them before this started, and I said I was going to list some patent numbers, but it would have taken too long. So we can talk about those in a bit here. And an interesting thing about Mr. John Burke is that he's worked on engine management PCBAs for not one, not two, but several F1 race teams. That's kind of cool. And he's a member of the United States Press Agency. I'm going to have questions on that in a bit. And let's see, it says EMS badass. Is that self-proclaimed, or did we call you that?
I think you called me that.
Well, it's welcome to the show.
Thank you.
Welcome, and thanks for joining us, John. I'd like to give you a second to maybe give us your version of the bio and maybe why it is that I was inaccurate in saying that you're in Santa Clara.
My version of the bio. So I've been manufacturing all my life. I'm now 72 years old, for the record. Started assembling electronics at the age of 16 on weekends, doing weekend work in a factory. Went on to just get into manufacturing generally, everything from missiles to mobile stuff. Much younger then, of course. And then when surface mount came along, late 70s, early 80s, put together the European version of the SMTA. Actually, that European version is now the European arm of the SMTA.
Oh, wow.
That was the Smart Group, Surface Mount and Related Technologies Group, started in 84, same month, same year as the SMTA. But about 5-6 years ago, the remaining directors of the Smart Group decided, hey, we've had enough of this. We want to retire, go have some fun. So they actually passed it across to the SMTA for management, and that's now the SMTA Europe. But obviously since then, I've been doing a lot of work on surface mount. Put my first double-sided surface mount board together in 1985.
Wow.
Yeah, I know. Yeah. Double-sided memory modules, line cards in 89. So
Now, was that with glue to dispense the components down and through the wave, or was that reflow?
That, in the case of the memory modules, that was double-sided surface mount. In the case of some of the boards, it was clearly, glue and wave solder.
So in those early days of surface mount, how were you depositing the paste onto the PCB lands?
Great question. The reason I got into that was I developed a patent for pre-gluing the circuit boards using a high-grab acrylic adhesive. Published that. The problem with publishing that was Loctite Research immediately read that and hired me as a consultant. But at the time, it was just like a dot dispense down. Actually, we did a lot of work on that and found that the reliability of that is quite exceptional. When you actually put the dot of adhesive down, as it heats up and cures, it expands and it actually spaces the components slightly off the board in some cases. So it was an interesting time.
How were you applying that dot? Was it on a gantry of some kind, or was it through? Okay.
Yeah. Yeah, the old machines were quite flexible, although mind-bogglingly slow. I mean, try 3,600 components an hour.
Yeah.
Yeah.
And in your memory, when did you start changing strategies to a screen printing technique?
So there have been gaps. I mean, I've been running from the bio several contract manufacturing companies, but screen printing, I don't think I ever screen printed the adhesive. I think I stencil printed the adhesive.
Sure. Sorry, using the term interchangeably.
Yeah, so that would have been about 1989, 1990. Yeah.
On a brass stencil, I'm imagining.
Well, it's interesting that being this old, I observed the history of things like stencil development. The first laser stencils actually came out of Scotland, unbelievably. There was a guy up there who had an etching shop, put in the first laser stencil, patented it, and eventually it got sold across the world. That was in 1990, I think. Also, the first high build nickel stencil came out of a company just out of London. I've used all of them. Definitely interesting.
There's somebody listening that's going to be really happy to hear about the Scotland reference.
We all thought the same thing. Yeah, we have a big fan of Scottish pride and Scottish heritage, and he would love to hear that part.
Well, you'd be interested to know that all these years later, John, I have a piece of Scottish-made equipment, laser equipment. So they're still keeping the tradition proud over there, still producing good laser equipment.
Yeah, and it kind of, goes back to where we are today in this world with Europe creating such, new technology in all of those forms that you just talked about. It's kind of weird that they wouldn't be a powerhouse still to this day, as far as, because I've seen their PCB factory numbers, right, just declining. I don't know what's happening with their EMS. I would assume the same thing. It's just weird that it wouldn't hold still throughout the trajectory of time almost, and
it can't. I mean, if you look at the cost of electronics, unless you fully automate, the industry for years has been chasing cheap labor. So, we saw the growth in Scotland. Actually, Scotland had capital from the British government. It was basically a development zone in Scotland, and that meant that many companies came in, America included, and said, "Hey, we've got a cheap manufacturing zone here. We can buy the equipment, the government's going to pay for it. Yay!" But eventually that went off to Eastern Europe many years ago. So, when the Eastern Bloc opened up in, was it 1991? A lot of the manufacturing in those countries moved into the Eastern Bloc for cheap labor. And of course, then you've got China. Actually, from the US viewpoint, originally they were building in Singapore, because you wouldn't do it these days. Then it went to Taiwan. I actually was in a Singaporean factory as they were moving the equipment into Taiwan many years ago, back in, I think it was 93, 94. And then, of course, Taiwan's so expensive, so it goes to China, and then squirrely things happen with China. Basically, it goes to Vietnam. And now we've got a huge import tax on Vietnamese goods, which will work itself out, I'm sure. So, it cycles round. If you look at the low-cost areas, that's where you'll find electronics being built, unfortunately.
That's a good point.
At high volume, especially. Right.
Yeah, and I always go back to my TV, right? If my TV, I had a 70-inch TV in my conference room, and I paid $300, $280 for that thing, right? If that same TV was made here in the States, it'd be a couple grand, right? And I don't want to pay a couple grand. I want to pay a couple $100. So consumer electronics, I understand, it's not just about the price point of the cheap labor, it's the price point to the end customer and what they can afford.
Sure, I agree with you, but the other thing you've got to think about is not just the electronics. Well, it is electronics, obviously, but you've got to talk about the glass technology, the screen. I mean, a lot of that
for the display.
Exactly, a lot of that product comes out of Korea, and they do have the screen technology for the display. Now, to the point, for your TV, would you want to manufacture the electronics in the US and ship the screen from Korea? I don't think so. I mean, the shipping logistics of a 75-inch piece of glass.
I think that's a good point, and something that is maybe painful for us Westerners to admit is that it's not just about cheap price anymore. There are certain areas of the technological spectrum that we've been surpassed on, right? There are third world or developing nations that are producing certain items not only cheaper than us, but better than us, right? And it hurts to say that, but it's absolutely the truth.
I agree to some extent. I would point out that in a lot of cases, the technology was developed in the Western world, particularly in the US, and decided, okay, we're going to go build it in Korea, we're going to go build it here, there, wherever. The only truly captive market in the US right now is defense. That ain't going anywhere. And I've built plenty of it. It's simply not going anywhere.
Some medical too, right?
Some medical,
aerospace.
But that's the decision based on the OEM. I'm sure if they could find a vendor that they had absolute faith in and needed to cut the cost, because some companies have got enough margin they don't need to, then they would move it offshore. But I'm excited with I'm not excited with the tariff. So I think all the prices are going to go up. But if it brings, to some extent, if we can get a reasonable agreement universally, whereby we can bring automation, high-level automation into electronics, or high-volume manufacturing of electronics, that would be a good thing. I saw it all go away. I saw it all go away back in early 2000s. It was incredible. I walked through acres of pick-and-place machines, idle, after the dot-com bust.
Couldn't give them away.
They couldn't. Well, they sold them. I mean, I went through several Selectron plants, Flextronics plants in Silicon Valley. Unbelievable, completely shuttered. To walk through there, as you walked along, the light came on in front of you and it went off behind you. And that equipment either got shipped to their facilities in the East, or they got sold off. And it's very difficult to bring it back. I mean, the sheer capital alone.
And for me, in the areas of like trying to compete, I took a Lean Six Sigma course. Elias took one too.
Yeah, most people
Pause and looks at someone else. But we're trying to figure out and Daniel's going to be a part of this study that we're doing recently that's all Six Sigma at my shop, kind of trying to find defects into it, right? And so if you were to, but the high mix part of it made it so tough when I was in those classes, because I don't run the same product over and over. Like they talked about using a Red Rabbit for a board, right? And I was like, well, that's okay, but if I'm running 30 pieces of something, to find out my standard deviation, and that by the time I get my program dialed in, that's it. I have no more boards to build and test on. How would you do that in an environment like where we're running a high mix, low volume?
It's very difficult. The reality is that, we talk about AOI, AXI, this, that, whatever, automation, SPI. In fact, the first time you build that board, when it goes through, truly you don't have AOI, because you haven't got a board to develop the program.
Right.
You don't have Flying Probe because you don't have the board to develop. You've got all these half-developed things that are there to make sure that your process is in control. One thing I will say to you, and I'm assuming that you're going to get a second run at those boards, the most important thing is extremely capable front-end engineering. If you've got that engineering expertise in the front end, you get a good product out of the process. Now, having said that, you can't control the design. You should have been giving a DFM report to the OEM before you even tried to build it. And the reason you should have done that is when you build this thing and it comes up with a bunch of rework due to the design, he's not going to want to hear about the fact that you need to charge him an extra $20 for the rework time. So that's why you run DFM up front. You can actually highlight and say, hey, dude, this is going to cost you a few extra bucks. Try and spin it next time round. But it is what it is. The most important thing is to do the DFM and do a post DFM. In other words, when you built that thing, whatever went wrong with it, don't just rework it. Make a record of it. See how you can improve it on that first run. And that will help you to tune the processing for the second run, where you can maybe do a slightly higher volume and, check your SPI records and everything else. It's all about data. It's all
it
about
really is.
front-end engineering and data.
Having a better understanding of all the processes, and that front-end engineering is even more critical in a high-mix, low-volume environment, because that first pass yield, I mean, your first boards that you're running are going to represent a large overall percentage of the total lot in the entire batch. So it's kind of even more critical.
It's all about people at the end of the day. You need good engineering front end. And also on Six Sigma, what do you to the point I was basically asking what you apply your Six Sigma to. It's not just about the
I wanted to start
yield. It's about the cost, the efficiency, as an example, how do you benchmark your receipts of material? Is it -2 days, +0? What is it?
Yeah, well, I'm starting from the blank, so I wanted to start with small with the SPI. So I wanted to start with basically, if I'm printing every single job and I'm noticing that I have to offset my print stroke on my forward stroke every single job that I have by a certain amount of millimeters, right? Or if another one is in the backstroke is a certain, then I want to change my global offsets on that, right? So I wanted to start with something small like that, just X and Y, right? And then we can get into the Z after that. But that was where I was going to start with, because then I could apply it to any board, right? Because it should be a standard calibration of, it should give me this based on that, right? So that's where my first project I was going to do on was just going to be on the SPI results and what my printer was giving me. That's where I wanted to start with.
Okay. So that's kind of interesting. It's doing on every design. Yeah, it's got to be the printer calibration. The reason I say that, well, it's either the printer calibration or the camera, one or the other.
It's more like a maintenance issue.
Yeah, it does. But one thing I would advise you, when you get to the Z-axis, be very careful how you set those limits. A lot of the industry is going minus 50 or -70. -50 or -30, up to +50 or even +80. Now, if you take those limits and you run a modern printer, you're actually running a CPK of 4, which is absolute lunacy. So when you set those limits, set realistic limits.
Okay. Yeah, you'd be happy with 2, right?
You'd be more than happy with 2. Yeah. But, I see it time after time when people start, and they do start with the printer. It's very common. They start with the printer and they say, okay, I'm going to go, -50 +80. Well, a modern printer, if you do that, you're going to get CPK of 4.0. Everybody gets a pat on the back and a bonus at the end of the year. It means nothing. Absolutely meaningless. Yeah.
Yeah, I think to the point of Sean's question with, low volume, you talk about DPMO, you'll never realize it with most of your lot size, right? I mean, when are you going to get to those million opportunities, right? So I think it's interesting to think about how can you find commonality in multiple runs, right? So can you look at it on a more granular basis? Can I track DPMO on 0201 components or 0603 components, right? Because over all your assemblies, you will run those in that range. So maybe it takes an adjustment in how you frame or how you analyze or where you pull your data from. Is it lot to lot, or can you find commonalities and track it over a broad product basis?
Do that. The only issue with that, when you're talking different products going through, so say you take 05, 0201, you decide that's what you're going to track. Okay. Now, a big factor into the performance of those components is the design of the footprint.
Sure.
They're not always the same size. Maybe one time they're copper defined. Maybe the next time they're solder mass defined.
Maybe the board design itself is going to induce tombstones, so that's not going to be a good representation.
If the component's hanging on by the skin of its teeth, it's just about making the pads, and then the pick and place machine is slightly off. You're going to get tombstoning all over the place. So yes, you can collate, if you will, between the component types, but you have to be very careful about how you extrapolate that data based on the pad design.
You also don't actually need a million opportunities to have an effective understanding of what your process DPMO is, right? I mean,
no, you don't. If you've got the experience, I've had some interesting conversations with some very high up people. Let's put it that way. I'll give you an example. And I'm not going to mention companies. Okay, we were having some issues with a very large customer on low melting point solder. I wasn't actually in that division at the time. I was in a different division, but they called me in after 5 weeks. And I went to the meeting and I looked at the data and I said, okay, your reflow profile's wrong. And they said, no, can't be. I said, no, it's the reflow profile on the warpage. And a week later, a bunch of PhDs said, no. So eventually the senior director...
in what sense? They were going too hot, too cold for the low temp solder? Or what?
No, it's a question of timing. The low temperature solder is a diffusion process. It doesn't. The low temperature solder melts. The SAC 305 does not melt. So basically you're talking a diffusion process between the low temperature solder and the solder ball. So unless the diffusion equation is based on temperature and time. So normally you talk about time above reflow. There should be a different term for it, but it's actually the same thing. So they needed actually extra time at the melting point temperature of the low temperature solder to allow the diffusion ratio to get to the right level in the 305 ball. But
I'm going to jump. I don't want to derail you too much, but I'm going to jump in and make myself a little vulnerable here. You just said SAC 305 doesn't melt. So how do you describe the physical condition or state of the solder when it's above liquidus? If it's not melted, what is it?
No, so I was referring to low temperature soldering. And in low temperature soldering, you're using tin bismuth or tin bismuth antimony. Actually, I found that the antimony is more reliable added to the tin bismuth. And that, like I said, it's a diffusion reaction. So the SAC 305 ball is not melting. It's actually having the tin bismuth antimony material diffusing into the ball. And the thing about, I know that you wanted to know about low temperature soldering. The main issue with it, people talk about it and say, oh, it's the warpage of the component. It's this, it's that. Yes, it is the warpage of the component. The reality is the solder ball never collapses. So, all I can say about that is that the collapse of the solder ball in conventional lead-free or leaded solder is the reason we don't see a lot of heading pillow it's because of the ball collapse. Now, if you take it and try and do the same thing with low temperature solder, you'll find you can get a lot of heading pillows simply because that solder ball is not collapsing. The warpage of the component is taking it out of contact with the soldering material. So, it is what it is. Like I said, a lot of upfront engineering needed. Or a lot of gray-haired observations.
When you say a lot of upfront engineering needed, that kind of brings me to one of the things we wanted to talk about. At least I did. I've at least tried to keep it together and waited as long as I could to talk about F1 to entertain these other questions. But I have so many questions when it comes to circuit boards in that world. So, I'm wondering how many layers they must be. Surely they're conformally coded, right? They must be to go into that type of environment. And how many circuit boards are we talking per car in a modern F1 vehicle?
A modern one, I'm not sure. I mean, all I worked on was the engine management. which was basically one board at the time, with some very, very heavyweight copper in the middle. I can't remember. I think it was like 8-ounce copper layer.
That's a good one.
That'd be
well,
fun to solder too.
you think about it. I mean, you got the fuel injectors. They're pulling huge amount of current for a very short time, and any resistance is going to change the output. I remember going to the lab at McLaren. They had a chemical bench. It was a very long chemical bench with a fume cabinet. On that cabinet was the wiring harness with the fuel injectors. At the end of that was the engine management system, and they were running it with, it's like a fuel equivalent, same viscosity, same. And underneath each one of the fuel injectors was a weigh pan, like a weigh balance. So they run this thing and they check the weight, and then they tune it and they check the weight, and they tune it and they check the weight. These guys go to extreme lengths to tune up these cars. It's unbelievable.
Just to get one little iota of advantage, right? I mean,
Yeah. And, to speak to that, there've been some absolute disasters in the industry. I mean, you may not remember, back in the Honda Williams, they developed the active ride suspension system. And what that simply meant was, as the car hits a bump, suspension retracts and then fires back down again. They were winning every race on the circuit with that thing. Every race. I worked on that too. But we were watching the, I think, I forget which Grand Prix it was, and the Williams car went up a straightway, over a rise, came down the other side and smashed straight into the wall. Killed the driver. Killed the
I
driver.
bet.
Wow.
Daniel laughed too. That's horrible.
And that is horrible.
Yeah, but what you got to remember is 2 days before that, the Formula One banned the use of active ride suspension.
Oh, so they had been used to that. Their driving style had been totally affected by it, got used to it.
Yeah. I mean, you think about it. You're coming up a straightaway, you're going to go over a hill, you're going to drop down the other side. The suspension's going to take care of it. Suddenly, you've just grabbed air, basically, with standard suspension. Not a good idea sometimes in a Formula One car. They're designed to stay on the ground and be pressed hard into it with spoilers and stuff.
That's interesting, though. I mean, obviously, that's a tragic story, but active ride suspension is probably commonplace now, or maybe even dated at this point, right?
Yeah.
But it's interesting to hear how the racetrack was the birthplace of something that just became part of most modern vehicles at one point in time.
Yeah, I think it was developed. I'm not sure that Honda Williams developed it. I've got a feeling it came out of Lotus in the UK. And of course,
we just went to.
You got Bose, I think, is doing a lot of work on it. You think they make headphones? No, they make active ride suspension.
Oh, wow.
Well, and now you've got magnetically controlled suspension, and I mean, it's just it's pretty wild.
Yeah, everything moves on.
We just went to a reliability, like a conference where they were talking about reliability and cleaning and harsh environments and really kind of pushing products to the edge. So that kind of environment is really well suited to understanding how any flaw or weakness in the design of the circuitry or how it gets assembled is really going to get exposed in that type of harsh environment where the performance is that demanding, right? So how densely packed are the circuit boards on an F1 car?
I don't know at the moment. I can tell you how densely packed they are on some military equipment.
Yeah, we'll take that answer too.
Extremely densely packed. I mean, it's unbelievable. I've actually seen package on package in those things as well.
Wow.
Probably no silk screen then, right? Because what would even be the point? You couldn't see it if there was one there, right?
I've been an advocate of taking off the silk screen for years, but yes, they still have silk screen. Silk screen is the enemy of good printing.
Yeah,
sure.
Yeah, you
There
want to
you go.
prevent a good gasket? Glob up a bunch of silkscreen on there.
Yeah. Actually, back in it was 91, 92, I actually etched the silk screen into the back of the stencil mirror imaged. So basically, you know, it was on a 4
Yeah,
or
to
5 mil
relief.
stencil. Yeah. So basically, the silk screen ended up buried in the stencil, basically.
Sure,
In the back
maybe
of the
20,
stencil.
25 microns deep or something like that.
Yeah, but I had to grow the image back then because there was no direct laser imaging of the legend ink.
That's kind of what you had. That was kind of your idea, wasn't it, Sean? Like kind of the similar idea.
My idea was to remove the
Yeah.
mask where the silk was going to go. And that way, when you applied your mask, you would expose it and you'd have your open areas of silk, obviously. But then you would apply your silk screen and then it would be on a level playing field of silk and mask, is because there would be the bare FR4 substrate that the silk was applying to. That was my
Yeah,
thoughts
so
with it.
Sean was talking about dealing with it on the board level, whereas what John was just describing
On the
is
stencil.
to make the stencil so it can basically
Yeah.
nest in that silk screen.
I don't know what. Yeah. Sorry, Elias.
I was just going to say that there's similar instances where we still to this day will etch reliefs into the backside of the stencil, like if there's a label or some kind of raised area and it's going to prevent the stencil from making intimate contact with the PCB, you can just mill out an area so it kind of nests in there
Sure.
perfectly and you still get good contact.
Yeah. Exactly. I think I was doing it in 92. 90. Yeah. But Sean, to your idea, that's a great idea. I'm not sure how that would affect the signal integrity.
If it's onto copper, if it doesn't have.
Well, so the thing about the solder mask is it's got a certain permittivity for a high-speed signal, and I'm not sure whether you would cause any problems by replacing that with the legend ink.
Well, you
In
could,
certain places.
instead of using silk ink, you could use white mask. You wouldn't have to use silk if you didn't want to. You could just use white mask.
Yep. And you could very accurately image that as well. With the direct laser imaging these days, it's
more accurately than the way silkscreen is applied, right?
There, you both use the same laser.
You do use the same laser. I've had to use that many times. I mean, the most complicated circuit board I ever built was 80 mils square.
With placements on it?
Yep. Flip chip. Yeah.
Don't breathe in too deep or you're going to lose your board in your throat.
Well, it was horrible. The company came to me and said, "Can you build this?" And I said, "The way you've designed it." So I kind of redesigned it for them with local fiducials. But
was that the one with 2/10,000ths of an inch of tolerance?
2/10 of a thou tolerance, X and Y.
5 microns.
Yeah. So basically, it was laser cut. We left it as a panel, laser cut them out. Needed 2 lasers.
20,000 up on an array at that size.
No, it's 10 by 10. 10 by 10.
So how big was the whole panel?
Not very big. Fiducial marks. The individual fiducial marks for each cutout took up more space than the actual board.
Yeah, I'm not imagining like traditional 1 millimeter size fiducials on there. They must have been quite a bit smaller.
No, we put the fiducials outside of the panel. So if you can imagine, you got a 10 by 10. Like I say, the fiducials took up more space on the panel than the actual cutout board.
It's insane.
I'd love to see a picture of that.
So you're not going to have any individual circuit fiducials.
There was only one placement, one flip chip.
Sure.
But it was interesting, and we built it. I think we got 97 X100 at the end of the day. We would have done better, but it was edge plated. So the board was edge plated. So basically, it was milled out. Part of the circuit was milled out for contacts. They edge plated that and then did the rest of the circuit. So basically what we were presented with was a blank panel with a gold-plated slot in it times 100. So that gold-plated slot had to be 2 contacts. So when we milled out with a regular laser the circuit board, we had to use a CO2 laser to break that slot into 2 for the 2 contacts, because basically that was how they powered up the circuit, those 2 contacts. Horrible design.
It just gets worse and worse from the PCB fab aspect the more you talk about this.
Sean's having trauma.
Every nightmare is like, oh no, because I mean I was at like no bid thinking about this thing like 5 minutes ago. Now
Yeah, so that's what I did. So we put it together. We didn't have a laser cutter. We didn't have underfill. We didn't have. Oh, by the way, it was underfill. We didn't have anything. It had keep out zones because it had to go into a slot. It was horrible. And they said, "Okay, can you make it for us?" And I said, "Sure, $15 each." This is back 12 years ago, right? And they said, "Oh no, can't do that." So I spoke to a guy a couple of weeks back. I just met an ex-colleague who, it turns out, he actually ended up building it. I said, "How much you charge him?" He said, $15.
Oh, wow.
You
bring up lasers. You have something in your bio about being involved in the development of lasers for whole soldering. Sean, the first time he heard that as a phrase, thought we were making it up. So we have a real expert here who can talk about it.
No, it goes back further than that. I mean, I've got to challenge anybody that listens to the podcast. When do they think the first public exhibition of laser soldering was?
It still feels
Can we do
new.
Price is Right style right now?
I demonstrated laser soldering inline on a real product in an exhibition in London in 1987.
That's insane.
What? No way.
Yeah.
What's old is new, right?
Yeah, that was a laser from a company called Basel Laser Technic in Switzerland.
So this one of the brands that makes stencil lasers, and it's the brand that we use. It's called LPKF. Their very early machines had Basel lasers sources in them.
Yes.
I never worked with them, but I've seen pictures and heard stories.
Well, the funny thing is, I met Carl Basel as part of that development. And I walked into his office. No joke. This was in 87. Calculators were normal. And on his desk was a slide rule. Talk about old school. Yeah. Yeah. So funny.
Yeah, it's
so to address your point.
For through-hole soldering?
Through-hole soldering, yeah. So some years ago, a company that I worked at, the plant in Malaysia, if you look at memory, if you look at enterprise memory that goes into computers, into server farms, into whatever, it's called an SSD, solid state drive. Historically, they had tantalum capacitors in them.
Okay.
It's backup. It's called a scram backup. What does scram mean? It's like a power outage event. It's called a scram backup. So basically what happens is when the power goes out, those caps are there as a short-term battery to back up the room. Those caps were costing, on a typical board, an extra $8 compared to an electrolytic. $8 per board. Compared to using a couple of
But they perform way better, right?
Well, not really. The electrolytic caps perform just fine, but they're through-hole.
Okay.
So we looked at it and said, okay, we've got these fantastic high-tech lines in place. What can we do to solve this problem? So we developed with a company in China, actually, we developed this whole pick and place, well, not pick and place.
Insertion machine?
Through-hole, pick, form, crop, insert, and solder using a laser soldering system.
Yeah, you
All
built a
in one
Swiss
motion.
Army knife. Yeah.
Yeah.
Would it
Yeah.
would it populate the whole thing and then solder, or at every placement it was soldering it at that time?
No, the application there were typically only 2 capacitors. So we were using 2 electrolytics. So it didn't have to have, huge potential for putting multiple components down in different places. It was just putting the same component down in different places and very few of them. But yeah, it was laser soldering.
Yeah.
The only drawback we had with that was the imaging on the laser. So there were a lot of early hiccups with that, where the laser was kind of hitting in the wrong place, or the solder was feeding in the wrong place, but good engineering team over there, they debugged it.
But you were just loading a reel of that part, and it would pick it off
Ammo.
of there and form
Yeah, an ammo pack basically.
and crimp it and form the lead and everything exactly how you wanted it, and then
Yeah.
feed wire solder to it and laser solder it at the point of contact. And
Yep.
yeah, I mean, simple really when you think about it.
Well, we tried to work with some. We tried to work with some companies that did conventional through hole, and said, hey, we want you to work with you and get a machine, but it was just too slow. It took. It was right in the middle of COVID. Actually, we started the development in. I'm thinking about June time in 2019.
Mm.
And the equipment, I think, was installed about August 2020, right in the middle of COVID, which was a really difficult bring up because the Chinese engineers couldn't travel.
Sure.
So the team in Malaysia, had to work on video conferencing while they're trying to bring up this machine. Fun times. Glad I wasn't there at the time. I couldn't travel either.
So it feeds a wire to it while the laser shoots at to solder. All right,
Yeah.
because I was always ahead before you mentioned that, Daniel. I'm like,
Yeah.
all right, so the leg's in there, but then where's the solder getting to? Is it just like bonding it to the whole wall of the?
It's a wire feed, basically.
Like a welder.
Yeah, pretty much.
Mm.
It's like a soldering iron, except it's using a laser instead of a optic. And the reason we did that, and it may have been right, may have been wrong, but when we looked at the other methods, there was an awful lot of maintenance involved. Should we have gone selective wave? Should we have gone wave solder? Should we have gone robotic solder? Everyone we looked at, there was a lot of maintenance involved. Soldering iron tips, wave solder, maintenance. Selective wave maintenance. So anyway, that's what we ended up with. I'm not sure they're still using it.
Have you ever tried to put your finger under the laser to see how hot it really gets?
No, but I
just
saw
curious.
somebody that did.
And that was enough, right?
It was hilarious. Back at that exhibition in '87 I told you about, the laser hookup, it didn't have a SMEMA interface. Well, it did eventually. So they were trying to hook between the pick and place machine, the laser, and then the downstream cleaner. And it wasn't quite working. And at one point, the engineer had all of the interlocks locked out. So not locked out. So he's got little clips and pegs and things so he could work on this laser while it was still live, which is completely against the health and safety rules. And we're standing there and we heard that, ouch! And the laser went through his fingertip. And
Like
went
all the way
straight-
through?
all the way through and cauterized on the way.
What
Wow.
wattage
Nice and
laser was
sterile.
this?
I think it was, let me think at the time, 60 watt YAG, I think, at the time. Yeah.
Running at
Yeah.
60 watts, or probably be
Yeah.
somebody lower than that, right? Maybe
No, probably around there.
max. That's For
It's only a 25 micron beam, so basically the way it works, I'm not sure people understand how it works, but you don't just hit it with a laser because you just splash solder everywhere. What you actually do is you run the laser through a Lissajous figure. In other words, you're winding it backwards and forwards in a Lissajous scan all the way down the joint. That's how it works. But in this particular case, he just fired off the laser, and he ended up with a 25 micron reminder.
At least it was
So-
cauterized right away. That's a plus.
I was going to give you guys a frame of reference. Like, to cut through millimeter stainless steel, we're only using about 18 watts, maybe 20 watts of power. So imagine what 60 would do.
Yeah,
1
actually,
millimeter stainless steel.
Thinking about it, that 60, that's a double-ended tube, so it's actually 230-watt beams.
Yeah, I've never experienced a laser on skin, and if I did, it was only 5 watts, but I never have, and it wasn't that bad at 5 watts, but I've never experienced it.
No, I don't think it's recommended,
Well, I think this is I think Sean's still stuck on how you get the wire to it, and if I know anything about Sean, he's not going to recover. Like, he won't sleep tonight. He's going to be thinking about laser soldering all night long.
Yeah, I hope you didn't leave him any of your contact information, because that will be
he'll call you.
that will be the worst
Time
mistake
zones
of
be
your life.
damned. This has been super fascinating. I think just the expanse of your career and all the different areas that you've been involved in, and learning about how, some of the things that we feel like are so novel and contemporary are really not that new and have been going around since the late 70s or 80s. And I think that's pretty cool to learn about. So thank you so much for your time. We really appreciate it. If folks want to get in touch with you, if they seek your services, here's your chance to let them know how to find you and kind of tap off some of this expertise that you've displayed here tonight.
Oh, so how to contact me? Fly to Vietnam. No, seriously, I've just been here in Vietnam building the house for the mother-in-law. Normally, I'm based out of Silicon Valley. You can find me on 408-518-1496. That's 408-518-1496. My name is John Burke, and I do consult in electronics manufacturing, particularly when high reliability is required.
You can
And thank
find him
you.
on LinkedIn too. That's how we all found him. So take a look at his profile there. And thank you all for tuning in. If you enjoyed this episode and would like some more, like, subscribe, all that good stuff. And we want to remind you about the SMTAI event that's coming up in October. And we will be in attendance in booth 2403. We'll have the full mobile podcast studio all set up. So we'd love to see you there. If you haven't registered yet, we encourage you to do so, smtai.org, and we'll catch you on the next episode.